Welcome to Chemistry with Caroline. In this video, we're going to look at cis-trans isomers. So cis and trans isomers are stereoisomers, which means that they have the same molecular formula, the same connectivity in the molecule, but a different spatial orientation. So remember, the molecular formula is just a description of how many of each type of atom are in the molecule. So CX, HY, maybe you add some heteroatoms in there. So for stereoisomers, the way they are put together, connected, is the same, but it's just the 3D spatial orientation that differs. So let's go to the next slide and we'll take a look at what that would look like. So in order to have stereoisomers that are cis and trans, there has to be something in the molecule that's restricting free rotation. So typically that's going to be a double bond or a ring, so the molecule can't freely rotate, and that's what locks in a certain 3D orientation. So let's look at an example with double bonds. I'm just going to use a 4-carbon chain, and there are two ways that this 4-carbon chain can have a double bond in the middle of it, so between carbon 2 and carbon 3, so same molecular formula, same connectivity, but a different spatial orientation. And that's because these two groups that are coming off of the central carbons that are part of the double bond are stuck where they are. The double bond does not freely rotate at room temperature, and so you can see that in the left-hand molecule, the two methyl groups in this case are on opposite sides of the double bonds. Sometimes it helps to draw in the hydrogens as well, so let's do that. So we can see there's where our hydrogens are on this molecule, and then here's where our hydrogens are on the molecule on the right-hand side. So on the right-hand side, you see that these two methyl groups are on the same side as one another. So when two groups are opposite one another, we call that a trans stereoisomer. And when two groups are on the same side as one another, we call that a cis stereoisomer. So another scenario in which you could use cis and trans terminology would be on a cyclic system if you had two substituents. So let's say that I have a cyclopentane ring. I'm going to use wedges and dashes to show 3D orientation, stereochemistry here. So I just want to write a little key down here. So if you have a wedge like this, that's something that's sticking out at you. And if you have a dash like that, that's something that is going back. So behind the plane of the board or the computer screen, whatever you're talking about. So say I have two substituents, like two methyl groups. I'll just put the CH3 here. And it doesn't actually matter where they are relative to one another. They could be next door. They could be across from one another on the ring. If they're both on the same face of the ring, so they're both sticking up, or they could both be sticking down, then they're going to be cis to one another, just like when we had the two methyl groups on the same side of the double bond in the previous example. So any stereoisomer that has the two substituents on the same face as the ring is going to be cis to one another. So I'm going to use dashes this time, and I'll just use CH3s again. And just to illustrate a point, these two methyl groups, they don't need to be next door to one another. You're just talking about the spatial orientation of the molecule. So if we're talking about the spatial orientation of these two methyl groups here, we would call them cis. It doesn't matter that they're next door or not, right? They're across from one another on the ring, but they're both facing down. They're on the same face of the ring. Same with the left-hand molecule. These two methyl groups are both on the front face of the molecule. They're sticking out at us, okay? So that would be described as a cis relationship. And then just to be very clear, these two molecules are not any kind of isomers to one another. They have completely different molecular formulas because we have a 5-membered ring here, right, and a 6-membered ring here. So their molecular formulas are not even the same. They're just two examples of cyclic molecules that have two substituents in a cis stereochemical relationship to one another. So then if we look at the trans example, you just have to have one substituent that's up and one substituent that is down. And the stereochemical relationship between those two substituents then would be trans. Okay, so this methyl is sticking out at us. This methyl is going back. They are on opposite faces of the ring, and so they are going to be trans to one another. Okay, so lastly, I just want to reinforce that if you have more than two substituents on the ring, you can't use cis or trans because this is really specific to the only two substituents on the ring. So for example, if I had this molecule, I wouldn't use cis or trans terminology because relative to what, right? Like which substituent am I talking about? So this only works when there's two substituents on a ring. And the ring doesn't have free rotation, right? Because it's cyclic, it's connected back to itself. And so the two groups are stuck in their given orientation. They're going to be either on the front face of the ring or the back face of the ring, but there's no way to rotate the molecule in which they would switch sides. So this has been a look at cis-trans stereoisomers. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.